Here's a question that seems simple. If I take a heavy 10-kilogram ball and a much lighter 1-kilogram ball and I drop them at the exact same time, which one hits the ground first? Your intuition probably tells you this: the heavier ball, pulled more strongly by gravity, should land first. It just makes sense. But what if I told you that this intuition, an idea that feels completely obvious, is wrong? What if I told you that for over 2,000 years, almost everyone, including the most brilliant minds on the planet, was completely mistaken about one of the most fundamental laws of the universe? Pisa, Italy, 1589. A young professor, Galileo Galilei, was about to overturn centuries of belief. He proposed a simple yet radical experiment. He would take two objects of vastly different masses, a heavy 10-kilogram ball and a much lighter 1-kilogram ball, and drop them from the top of the tower at the exact same time. And in that moment, a profound truth was revealed. They fall together, perfectly synchronized, landing at the same instant. The reason lies in the mathematics. The time it takes for an object to fall depends only on the height and the strength of gravity. Notice what's missing from this equation. Mass. It has no effect. And with that, our understanding of the universe was changed forever. To solve this puzzle, we need to look at the forces acting on each object. The first piece is gravity. The force of gravity is proportional to an object's mass, so the heavy object experiences a much larger gravitational force than the light one. If this were the whole story, our intuition would be correct. But there's a second piece, Newton's second law. It tells us that an object's acceleration is its net force divided by its mass. Mass here plays a different role. It's a measure of inertia, or an object's resistance to being moved. Now, for a falling object, the only force acting on it is gravity, so we can substitute our gravity equation into Newton's law. And here is the beautiful, elegant moment where the paradox is resolved. The m for mass in the gravitational force and the m for inertia in Newton's law are the same. They cancel out completely. The mass of the object, whether large or small, becomes irrelevant. The result is that the acceleration for every object in freefall is exactly the same. It is equal to g, the acceleration due to gravity. The mystery is solved, but there's more. Let's set up our experiment to discover the mathematics that govern this motion. On the left, we have our physical experiment. On the right, a data zone where we will plot what we observe. As the objects fall, we'll trace their position over time. Notice they fall together, tracing out a single, identical path. The resulting graph is a perfect parabola. Now, what about their velocity? The velocity at any moment is simply the slope of the position graph. By tracing this slope over time, we discover another pattern. The velocity graph is a perfectly straight line. This visual discovery is confirmed by the equations of motion. The equation for position is a quadratic function of time, which perfectly describes a parabola. And the equation for velocity is a linear function of time, which perfectly describes a straight line. We didn't start with the equations. We discovered the mathematics simply by watching the motion, and we've confirmed once again that both objects follow the exact same patterns. Let's dig deeper. Let's explore the beautiful consequence of a single simple condition: constant acceleration. It all starts here. We assume that the acceleration of our object does not change over time. On a graph of acceleration versus time, this is a perfectly flat, horizontal line with a slope of 0. Now, since acceleration is the slope of the velocity graph, a constant acceleration means our velocity graph must have a constant slope. In other words, it must be a straight line. From this visual fact, we can derive our first kinematic equation. Next, since velocity is the slope of the position graph, a constantly changing velocity means the slope of our position graph must also be constantly changing. A curve whose slope changes linearly is a parabola, and from this shape we derive our second kinematic equation. These two relationships, born directly from the visual logic of the graphs, are the parents of all the others. Through simple algebraic combination, they give us the complete toolkit for analyzing any motion under constant acceleration. 5 simple, powerful equations, all emerging from one single foundational idea. We've seen how taking the slope of a graph, the process of differentiation, allows us to move from position to velocity to acceleration. But what if we want to go on the inverse journey? How do we go backward from a rate of change to the total change? Let's start with a velocity graph. The key insight is that the area under this curve, between 2 points in time, gives us the total displacement. The mathematical tool for finding this area is the integral. As we sweep our boundary from left to right, we are accumulating area. Watch the number line below. The value it tracks is the total area calculated so far. This accumulated area is precisely the change in the object's position. The exact same principle applies to acceleration. The area under the acceleration curve gives us the total change in velocity. We can set our boundaries, and once again, as we sweep across and accumulate the area, the number line below tracks the total change in velocity. This reveals a beautiful symmetry at the heart of calculus. Differentiation is the process of finding the slope. Integration is the process of finding the area. They are perfect inverses, two sides of the same coin, allowing us to travel up and down the ladder of motion. In 1907, Albert Einstein had what he would later call his happiest thought. It was a moment of profound insight that would ultimately reshape our understanding of the universe. The thought experiment begins with a simple scenario. Imagine an observer in a closed room, a windowless elevator, somewhere on the surface of the Earth. They are in a constant gravitational field. If they release two objects of different mass, as we've now established, they will fall together and hit the floor at the exact same time. Now imagine the same observer in the same room, but this time floating in the blackness of deep space, far from any gravitational influence. If the room is stationary, the objects will simply float. But what happens if a rocket attached to the bottom of the room ignites and pushes the elevator upwards with an acceleration exactly equal to the acceleration of gravity on Earth? From the observer's perspective inside the room, the floor is rushing up to meet the objects, and because the objects have no force acting on them, they are hit by the floor at the exact same time. The crucial insight, Einstein's happiest thought, is this. From inside the room, with no windows to the outside world, these two scenarios are completely indistinguishable. The experience of standing in a uniform gravitational field is identical to the experience of being in a constantly accelerating reference frame. This elegant and powerful idea, the equivalence principle, is the very foundation of Einstein's theory of general relativity, which describes gravity not as a force, but as the curvature of space-time itself. This single elegant principle that all objects fall at the same rate regardless of their mass has profound consequences that shape our world in ways we see every day. Consider satellites in orbit. They don't stay up because they've escaped gravity. Quite the opposite. A satellite is in a state of continuous free fall. It has such a high sideways velocity that as it falls, the Earth curves away beneath it at the exact same rate. It is constantly falling but perpetually missing the ground. Now, what happens when an object falls not through a vacuum but through our atmosphere? Here, a new force comes into play, air resistance or drag. As a skydiver falls, their speed increases, and so does the upward force of drag. Eventually, the force of drag grows to perfectly balance the downward force of gravity. At this point, the net force is zero, acceleration stops, and the skydiver continues to fall at a constant terminal velocity. Finally, consider the path of a projectile like a cannonball. In a vacuum, the only force acting on it after it's fired is gravity. Since we know that gravity accelerates all masses equally, It means that a heavy cannonball and a light one fired with the same initial velocity will follow the exact same trajectory, landing at the same spot at the same time. From the silent dance of the cosmos, to the complex balance of forces in our atmosphere, to the predictable arc of a thrown ball, this one beautiful principle of physics is at play all around us.